Okay.
So welcome everyone. Just give a few seconds. This webinar is supported by the International Union of Radio Science and also by Engineering in Medicine and Biology chapter of the Czechoslovakia section of IEEE. And today I have pleasure to introduce Dr. Kevin Robin from the University of Iowa. Kevin graduated from Kansas State University in 2016 from a bachelor in chemistry, math, and physics. And then he attended graduate school at the University of Iowa, where he earned a PhD in chemistry work in the Chris Cheatham's lab. And now he's continuing as a postdoc in the group. So, Kevin, with this, I'd like to give space to you. Please go ahead.
Okay, thank you. Yeah, so today I'll be talking on behalf of Chris. I'll be talking about low frequency protein motions coupled to catalytic sites in FDH. So I'd like to start the talk with posing a question, which is, what timescales are important for enzyme catalysis? So in our biochemistry classes, we generally learn about these kind of long, relatively longer scale motions like protein breathing and folding that are important for situating the substrates for catalysis, docking of ligands, undocking, and things like that ordinarily happen, looking here at order of greater than microseconds to milliseconds timescales. And that's generally what we tend to think most about when we think about catalysis traditionally. There are, of course, faster events that we know happen, such as side chain movements, or even as fast as bond vibrations that happen on many orders of magnitude faster. So on the orders of bond vibrations are happening on the order of tens of femtoseconds, and then of course there's from transition state theory, there's the concept that the half-life of the transition state for catalysis is on the order of about 100 femtoseconds or so. And so it's interesting that's about the lifetime of the transition state, but that's on the order of 100 femtoseconds. But yet, what we think about as catalysis is happening in dynamics is happening many orders of magnitude faster. And so what the question I pose is, what's happening here, and does it matter or does it not matter for catalysis? And I chose this photo on the slide also because it also had a nice convenient plot of just turnover numbers to compare with, and of course is probably the best example of a very fast enzyme is catalase here at nearly a nanosecond. So we know that somewhere between that's the fastest that a reaction can happen. That we know one of the fastest that we know of that can happen is on the order of a nanosecond. But then we also have these questions of bond vibrations happening about three orders of magnitude, 4 orders of magnitude slower. And so we're trying to the question is, what's happening in this gap and how is it relevant to catalysis? And so to talk about that, I'm going to first, I'm going to tee up, a quick review of the activated tunneling model before I show you some other results from the field, from our field more generally, and put our research in the context of what some historical data first. So the activated tunneling model is a common model used for describing reactions of particularly light hydrogen and hydride transfers. So the general idea is that you have double well diabatic potential that starts with the reactant state on one side and the product state on the other side, and the coupling of the two diabatic states forms an adiabatic potential that when you cross over the transition ready state, you find yourself in the product state. And so in between with the transition with the tunneling ready state, you have this zone where you become degenerate, and it degeneracy allows for splitting and a faster rate of reaction. And so this is kind of just a general. I'm not going to go in too much detail here because what I really want to get at here is about the donor acceptor distances. And so this is also baked into the formula for predicting the rate of reaction where you have to consider the distance between the donor and the acceptor. And so there's kind of just another little plot here. Of course, when the donor acceptor distance is small, they're well overlapping, and you have a high tunneling probability between the two. And when you're, of course, when you're long, you start to, when the distance between them is long, you have a lower, the probability falls off. And somewhere in between this, depending on the situation, you will have a distribution of donor acceptor distances that describes, statistically where you'll be at. So in this particular example, we're looking at isotopes of hydrogen, so tritium, deuterium, hydrogen here. And this is just kind of a generic drawing that we've done where you overlay the donor acceptor distances and the tunneling probability. And it's the multiplication of the two and the integral over the multiplication that gives you a product that tells you roughly how likely that is a factor in how fast the reaction rate occurs. So the better the overlap between the tunneling probability and the distribution, the more likely and faster that the reaction will happen. So in this particular case, a generic case that you have, the distribution is kind of more towards the tail end of the sigmoidal shapes. You're going to have a different value for the integral. And so therefore the value for the integral between the product of the two is going to be larger for hydrogen and smaller for tritium. And deuterium's here somewhere in between. So what that basically means is that you're going to have a faster reaction for hydrogen than you would tritium. Okay, well, so that's pretty typical of chemistry and solution, ordinary solution phase. This leads to what's known as a kinetic isotope effect, which is that heavier isotopes tend to have an effect where they lead to a slower reaction rate, and that's exactly because of what I'm showing here. But there are so while kinetic isotopes effects are typically temperature dependent, there is an interesting finding in biology where, particularly with like hydride transfer reactions and hydrogen proton transfer reactions, that many wild type enzymes exhibit temperature independent kinetic isotope effects. So this is me teeing up a reason for why you should be interested in the talk, because the first time I learned this, I thought that was particularly interesting. Well, how is that possible? So I'm just going to roll back to this figure real quick and show you that. Imagine if this distribution were very narrow and peaked right around here. And so therefore the overlap between, the donor acceptor distance distribution and the tunneling probability wouldn't change between the two because the distribution basically would end somewhere over here, and it would be the same between hydrogen, deuterium, and tritium. So that's thinking, that's really the only way that this could really happen is if you have a very narrow and short donor acceptor distance that would enable that. And so that appears to be, that's the interpretation of many of these experiments where we find temperature independent KIEs. There is some sort, this implies that there's some sort of evolutionary pressure to form a short and narrow distribution of donor acceptor distances. I remember the first time learning about this being so intrigued. And that mutating the active site residues often leads to a temperature dependent KIE. So it kind of destroys, or rather broadens and lengthens that donor acceptor distribution, which leads to temperature dependence. And so what that means is that you're essentially, if you think about that in terms of dynamics, you've now mutated the active site, so it's far less compact and compressed and predictable to where it's more flexible and more dynamic. The really interesting thing here is that mutating certain distal residues, even as far as 20 angstroms away, has been known to cause temperature-dependent KIEs. So for some reason, mutating distal residues far, far away on the other side of the protein, there are many examples where this leads to an active site that is very different dynamically than it was for the wild type. And so in other words, this mutation of the distal residue will influence the conformations that you're sampling at the active site. And so I've kind of teed up some interesting some findings historically. This has been known for quite some time, and so it kind of begs the question of what's happening with dynamics at the active site. And why are they so sensitive to mutations far away or even inside the active site for that matter? So I want to kind of tee up another concept here, which is that we've observed throughout the last 40 years or so, that a number of scientists have published results over low frequency modes observed in a number of different proteins. So this is a sort of related concept that there should not be, as we would expect for things lower than KT, we would expect overdamped oscillations to be happening. So anything that's much less than KT would be up against a lot of friction, very low frequency modes that you would not expect to be very persistent and have a very we expect a lot of dampening to be happening, a lot of coupling. And so it's very interesting that when we observe narrow peaks in the low frequency region of proteins, that's something that's kind of hard to explain. So just citing some examples, this is even published from 1982 that kind of dates how the record of how long we've known of narrow underdamped motions in proteins has been for. And just one particular example more recently that I plucked out was from the this is data from the WIN group over in Glasgow. In 2014, they took the optical curve, so they used the optical curve effect to basically measure the Raman spectrum of, for example, lysozyme. And what they found is this beautiful large peak, very narrow underdamped peak, right around 2 terahertz. And so, if you were to compare that, for example, to just tryptophan in water, aqueous water, at the same concentration, and they chose tryptophan for a good reason. It's the with the polarizability that's most likely of all the amino acids has the highest polarizability, most likely to contribute to the Raman spectrum. At the same concentration, it does not at all seem to account for what's happening in the whole protein, collective protein. So so there's just further evidence that there are in fact underdamped oscillations happening on the orders of a couple terahertz, and converting that to wave numbers on the order of tens of wave numbers. So that's kind of placing the historical context of what's been known about underdamped oscillations and low frequency underdamped oscillations before we get to what our group has published so far. But now let me kind of tee up another introduction to pump probe spectroscopy, which is what we've been focusing on with our group. So pump probe spectroscopy, as I kind of alluded to earlier, is useful for measuring particularly fast processes. So looking again at the time scale of structural changes, proteins, we're looking on the order of bond vibrations and side chain rotations, and so that's where we're probing right now. Of course, there are other forms of pump probe spectroscopy that can go much longer time scales, but generally speaking, this is what I'm referring to. So how does it look? Well, pump probe spectroscopy is relatively simple concept. You first pump a sample and then you probe it sometime later. And so there's a delay between the pump. Oops, my cursor's a little jumpy. There's a delay between the time that you pump and you probe, and often we're interested in watching that delay. It's kind of like making a movie in some ways. And so pump probe spectroscopy, we normally think of as a one-dimensional spectra where you just look at the change in absorption between the pump on and the pump off. And so you're looking at the probe axis. So two-dimensional spectroscopies, they're going to go a step further. They are a form of pump probe spectroscopy, but they're going to resolve the pump frequency, which is a subtle difference here. So to kind of run through that discussion, imagine that we have the pump and the probe are overlapped in time. Wherever you pump at a particular frequency, you're likely to probe that same frequency there. Now, if you go ahead and you delay the time between the pump and the probe pulse, what you're going to have is dynamics. Dynamics will happen. And so what that means is molecules are going to bump into each other. Bond distances are going to shift, and correspondingly the frequency, the instantaneous frequency of vibrations are going to shift, and they're going to diffuse throughout a whole ensemble that you're likely to observe over a long range of time. And so what you're seeing right here is just kind of a cartoon illustration of me imagining that you're having spectral diffusion of a particular bond throughout a distribution that we characteristically see in a normal just infrared spectrum. So we're kind of picking apart that infrared spectrum into how long does it take for that one single sample to diffuse through the spectrum. And so the result of that is that where you pump a particular frequency now has no correlation over a long time delay, has no correlation to where you probe it. And so you're going to start with a correlation and you're going to end with an uncorrelated distribution. And so let's look at that more like a simple. I'm going to go ahead and run through a simulation of what that actually looks like with a two-dimensional infrared spectrum. So again, we have a pump axis here, we have a probe axis here, and what we're looking at, for example, is like a simulation of the thiocyanulated stretch of methyl-thiocyanate. And so the CN stretch. So you're, just kind of nice narrow peak here in the window the IR window region, and at zero delay between the pump and the probe, you're going to have a nice correlation between where you probe, between where you pump and where you probe. And there's a way to numerically measure this. So by the FAIR group came out with this, probably 12, 14 years ago now, which is the concept that you take the vertical slices along the probe axis at each individual pump, and then you just find the maximum. And so you find the center of the peak, the center maximum, and then you plot every point along the pump axis, and then you draw a line through it. And so you say it's slope. And so it's called a center line slope. It is a quantitative measure of correlation. And so the idea is you take that point, and at this example, we have zero delay between the pump and the probe, and I plotted it there, right there. And so you can now vary the waiting time between the pump and the probe, and what you'll find is it starts to decorrelate over time. So what we typically do in our lab is this is actually very representative of an actual measurement. We'll do that for a number of different waiting times, and then we'll repeat the measurement over and over again just for averaging purposes. And so this is very typical to what you would expect to see for like methyl thiocyanate in like water, for example, any typical solvent, which is in highly overdamped dynamics. So, right, because what we're measuring is essentially how long does it take for something to decorrelate, and you think of this as essentially what is, the dynamics that are happening to the oscillator that are causing perturbations in frequency. So it's very normal to see an exponential decay, often multi-exponential decay for measurements like this. To give you more context, let's change the solvent. So if I take these are actual data measured of methyl thiocyanate in water, for example, and glycerol, very slow solvent. You're going to see a very long CLS decay, very long dynamics. Ionic liquid that's a little bit faster, DMSO, and then water. So the centerline slope provides a very, very interesting way of actually piecing apart and measuring dynamics. Okay, so let's apply this to biochemistry. So one system that we're interested in studying is formate dehydrogenase, which catalyzes the reaction here of formate into, for formate makes a hydride transfer to NAD+. You can see the transition state right here, and then the product is CO2 and NADH. So this system is only interesting to us because it forms a very nice transition state analog with azide. And so azide is a beautiful infrared chromophore. It is a very, very bright infrared chromophore, which makes experiments for us a lot easier. So that's the main reason why we chose the system. So as an actual three-dimensional model here, you can kind of see, for example, here's the azide, this little cylinder right here, situated in the active site. Here is the nicotinamide ring of NAD plus right here. And you can see that they kind of just, bump into each other. There's also, I want to point out a particular residue right here behind the nicotinamide ring, which is valine 123. That is, we're going to be mutating that later on. So I just want to point out that that's kind of sits behind the nicotinamide ring, and it kind of pushes up against the ring and azide and smashes them together. Yeah, I just want to point again to the transition state real quick before I move on, that we have, what you have here is the same formal charges as the reactants have, and yet it takes the isoelectronic form of CO2, and so that's why it makes for a really great transition state analog. Note that this is negatively charged, this is positively charged. That'll matter later on when we look at some other results. Actually, this slide right now. So measurements of FDH for the centerline slope came out quite interesting. So remember earlier how I said we're expecting these exponential decays, maybe multi-exponential, but certainly overdamped. That is the norm in two-dimensional infrared spectroscopy, and most spectroscopies for something like this in a solvent. But that is clearly not what we observed. We observed some oscillations in our centerline slope, which means that there are, in fact, underdamped dynamics happening around the azide that are influencing the centerline slope that way. So the real question is, here our bioelectrodynamics talk. What happens if we change the Coulombic interaction between the two? If we swap out that NAD plus for NADH, what we see is that the oscillations go away. So it's signaling clearly there's some sort of Coulombic interaction that matters for or somehow influences the oscillation, brings about oscillations in the line shape. And so this is a result we published a while ago, 2016. But we've since then more recently changed, the experiment up. So let's do some mutations. So this goes back to the valine 123, where we, mutated from valine to a slightly smaller residue, alanine, and then of course all the way down to glycine. We see how does this change? How do oscillations in active site change with those different mutations, and also looking at the kinetic isotope effects. And so here we can see that there's a significant, so we also improved our apparatus where we can achieve a much higher signal noise here. So our SNR is much higher in this data. Here we can see, there's clearly something different about the oscillation. So if we go ahead and take the Fourier transform of this, then we get something that's like spectral density, roughly speaking. So we take the real part of the FFT and we find, that there is a sort of a trend here between this 9-wave number peak in oscillation and then if we, going up as we mutate from the wild type valine to alanine smaller to glycine even smaller, that this amplitude increases in intensity. And so that's kind of interesting. So I'll make a, in just a second, I'll kind of discuss an interpretation of that. I want to show you another set of data real quick, which is what if we were to plot this, the intensity of this 9-wave number peak up against the change in activation energy for the hydrogen tritium kinetic isotope effect. So as I said earlier, with wild types, you typically have a very small change in activation energy, which is kind of very interesting feature in and of itself. But we notice that mutating the active site changes the donor acceptor distribution in a way that creates more fluctuations, and the distance between the donor and acceptor increases and broadens, either one of those will cause a change in the activation energy. And so we're seeing that here, that there's a linear correlation between the intensity of the 9-wave number peak, which corresponds to more fluctuations at that particular, a higher intensity of fluctuations at the 9-wave number 9-wave number oscillation, and the perturbation of the activation energy between the hydrogen tritium isotope effect. So kind of using molecular dynamics, we're able to peer in and get some better ideas of what's happening with the donor acceptor distribution here. And so we also published on some molecular dynamics where we were able to see that indeed mutating the active site led to a donor acceptor distribution that was, both further out in average distance and wider in distribution. And so there's an explanation for why that's causing this, significant change in activation energy here for the isotope effect. So, and along with those same simulations, we were able to observe that there are indeed actually underdamped oscillations in our force-force correlation functions. So these are simulated force-force correlation functions acting on the azide, an active site. And so since then, one of the students in our group, Lauren Parr, has improved on the simulations, and I only notified her yesterday of the talk, so I wasn't able to get her data in time to show you, but they actually, the newest data is very consistent. It's remarkably consistent with this 9-wave number peak here, and so I wish I could show that, but it's just not in time. But we're improving our simulations and getting a better insight at the moment for this. So the next experiment we did right after this was this is the one that's most complicated, was to go ahead and see, what happens when we start with, changing the, the isotopes of the backbone of the protein. So for example, changing going from N14 to N15 in FDH, how does this change dynamics and so on with 2 other mutants? And so what we find is actually kind of interesting. So, here we can see with the unlabeled FDH, we're at, we have a relatively, this reminds us of what we just saw on the other slide here in the green. And that when we change to, for example, from N14 to N15, we significantly inflate the baseline of our centerline slope. So you can interpret that as meaning that there's a lot more inhomogeneity in the distribution sampled by the oscillator. So in other words, just a static offset is increasing means that we're observing a more heterogeneity in the conformations being sampled. But interestingly, changing from carbon 12 to carbon 13, keeping the N15 mutation mutant, that isotopolog doesn't actually change dynamics a whole lot. And so if we went and did the line shape analysis or fitting analysis on this, we don't really see a whole lot of change in dynamics here. The weirdest part about this result is when we then make the triple isotopolog, adding deuterium to this, and it somehow compensates the dynamics back to more like the wild type. So this is a very interesting result. Our current reasoning for this is to think that, well, okay, so when you go from so the CD bond is slightly weaker than the CH bond, which is going to lead to more more stable aliphatic regions in the protein. But at the same time that's happening, if you were to go from changing to the heavier N15, also weakens the hydrogen bond, which causes a weaker hydrogen bond. Weaker hydrogen bonds lead to more unstable parts in the protein. And so these two, we think, are kind of compensating for each other, where it's more, the aliphatic regions are more hydrophobic and stronger and more compact, whereas the polypeptide backbone is more loose and more dynamic, and so we think they kind of compensate each other in that way. And so while we're at it, why not look at some kinetic isotope effects? Change in activation energy versus 1 over the square root of the molar mass. We would expect that, if this is the simplest thing possible, that we could explain a change in activation energy as a raising of the 0-point energy. And so you'd have a linear trend here with the inverse molar mass. It's not quite that. You can see that it's somewhat nonlinear. But moreover, just the fact that there's no obvious trend here going on with dynamics, that, this seems to be something that can't explain simply by mass effects alone. There's clearly the inconsistency or I should say the non-predictable nature of the dynamics is clearly signaling that there's some sort of change to electrostatics that appear to be happening with the isotopologues, which is kind of unexpected. So that's kind of the latest experiment. Right now, currently, what we're working, kind of review is that we observe that there's, the addition of NA, whether we have NAD plus or NADH in our active site will change the dynamics. And the one that's more like the transition state currently brings about oscillatory dynamics, and taking that transition state analog away kind of creates underdamped oscillations or overdamped oscillations. Right now, what we're working towards currently is we're exploring different enzymes with allosteric effectors. So HIV-1 reverse transcriptase, beta-lactamase, and P38. Currently, the enzymes that we're making right now, and of course, doing this also requires an infrared label that is not azide. So we are having to move to much weaker infrared labels, which is making the experiments a little bit more difficult. But that's currently my focus right now, is improving the sensitivity of our apparatus. So we're going to be changing to more non-canonical amino acids, like with nitrile stretches in them. And so, we can probe those anywhere that we want in the protein instead of just at the active site, which would be more interesting too. And then, of course, we're going to take a deeper dive into MD simulations. And so I'd like to thank members of our group. Lauren Parr is currently working on a lot of these. She's the computational person in our group, is working a lot on the simulations. Nick Ludke is the biochemist in the group who is expert in making all these proteins. Evan Schroeder, and Whitney and I, all three of us are working on the spectroscopy side of things. And then, of course, our advisor, Chris Cheatham, who's been extremely supportive of us. And then, of course, our funders, NSF and NIH. So with that, I'd like to end the talk and be open to take any questions right now.
Thank you very much. Very interesting. I have quite some questions. I wrote some notes here. So I'm wondering if there are any here from the audience. I don't see any raised hand so far. Let me start maybe then. So maybe I first started to get some maybe more solid understanding how it actually works. We are not to do like pump probe spectroscopy, so let me ask maybe some basic methodological questions so I understand correctly. So I understand there is an enzyme, you have some substrates in the active site, right? which are converted. So how is it with these nitrile probes? Are they just the probes, or they are taking place in the reaction there? So, for example, in this case, you were showing that was the normal substrate was so that's CO2, or was it maybe in the slide 12 probably? Beginning there, yeah, there the probe stuff.
Yeah, let me go. There we go.
Okay, yeah, here.
Yeah. So the trick here, it's subtle, but it's important, is that we keep it in, we're using inhibitors. So we're trying to get this protein stuck in the transition state analog.
Okay.
You do not want it to move from there because you bring up the point of timescales. So if we're interested in looking at the transition state, then, well, it's only going to last for, on the order of 100 femtoseconds. And then of course there's no real chance of probing that within, the time range of every pulse, which is every like millisecond or so.
Okay.
So yeah, we have to get these transition state analogs to get it stuck in that analogous state.
Okay. Okay. I see. So that's what the SID is here basically is blocking the transition state. And
Yes.
and at the same time is a wonderful IR probe.
Yes.
Okay, I see the
Yes.
trick now. I missed the blocking transition state part of it.
Yeah. I want
Okay,
to.
okay.
Yeah.
And okay, so that means that you are basically getting the signal from basically from these bonds, so double bonds from from the probe,
Mhm.
but they can somehow respond to the obviously the motion of the enzyme, and that's where how we are probing that enzyme motions. Okay, okay, I see. Okay, now it's clear, at least to the level I need. I think I can ask further questions.
Mhm.
Okay, cool. So I was curious about in this particular case, in this formaldehyde hydrogenase, when you were showing these oscillation, I was in the slide 12. So I guess answers might come from the molecular dynamics simulation. So have you had a look on or maybe your colleagues there on what kind of motions of enzyme these fluctuations, these oscillations correspond to? Should be some global mode because they're very low, as you mentioned, right? Rather low.
Yes.
So
This is
9
a
wave
very
numbers. Yeah.
Yeah, this is the question right now that we are trying to answer. And Lauren Parr is the one who is spending her primary focuses in answering this question. She's got some so we're not like a computational group historically at all. So she's gone and done a lot of work with our collaborators and learning how to do all the computational work, and is really gotten to the point now where she can consistently simulate the oscillations, and so she's just now opening up a box of analysis and trying to figure out exactly if we can track down project out where these oscillations are coming from in the protein. As you said, is it a whole protein breathing motion? Is it, where exactly is the nature of the oscillation coming from, and how large, and to what residues is it originating from? That's currently what we're trying to figure out right now.
Okay, I see. Okay, cool. I was also wondering, maybe, it's something probably this goes beyond what your data can answer, but this is kind of discussion we have. So like, be free to to speculate or let's be open-minded here. So I'm wondering, there you made some mutations, which is, by the way, very cool stuff, to see how the particle mutations will change the enzyme, particularly its dynamics. And the two mutations you showed, they were affecting the amplitude, but not the
Mhm.
frequency.
Yeah, that's right.
That's actually very interesting. I mean, so would you have any insight in that? Why I was kind of understanding that, well, depends. If you have say if it's more like a more dominant motion of or say a low frequency motion of the protein, then at first what is interesting is that the single mutation, well, it depends on where it is, it affects it, because sometimes people say when the global motions are not that heavily affected by particular single mutations, but maybe they do if it's a really crucial site and crucial residue. And then if they do affect, then I'm just curious. It's a little bit interesting that why it only affects the amplitude and not the frequency itself.
Yeah.
Do you have
Yeah,
any
I
insight
had
to
the
that?
same question. What we've discussed so far, and our leading hypothesis is that looking at the size of the residue, we go from valine to alanine to glycines. We're gradually going smaller in size of the residue. And this is the residue that's sitting right behind the nicotinamide ring. And so in some ways we can, be careful about how I say this, but in some ways we're thinking about this as freeing up space for the nicotinamide ring to bounce around and enable. What I'm thinking here is more like a larger amplitude of the 9-wave number oscillation. So we're kind of, the assumption here is that the 9-wave number oscillation is associated with the nicotinamide ring bouncing into the azide reporter, and that freeing up that space behind it allows for a larger amplitude. swinging there. So that's kind of what we have so far. Yeah.
Okay, but that will be then addresses the thing that it's probably the motion on a smaller scale, as I mentioned, of the bouncing of the ring there. So it's probably
Yeah.
would not be corresponding to the global motion of the whole protein, or maybe there is some coupling within two. I'm not sure.
Yeah, yeah, and I try to be careful there because it's not like a vacuum opens up in space. When you do, something's gonna fill it. But you can kind of see the corollary there between reducing the size of that residue and certainly the amplitude of that fluctuation increasing. Yeah, I can't. I mean, right as of right now, we think that it's localized. We don't really have a lot of evidence that it's occurring on a global scale. That being said, we are trying to do mutations on further distal residues and see how those affect the fluctuation amplitudes right now as well. So that's kind of open question that we're working on.
I see. Yeah, because the kind of the story you started with was saying that, yeah, in one of the introductory slides, that even the far, let's say, there are distant, well, in some other proteins, of course, other enzymes, some distant mutations can affect the dynamics somewhere further, which would kind of imply there is a global mode involved. But it's, of course, the things can be much more complex in this particular case of yours.
Mm-hmm.
Okay, I see. I would like to also ask a question about these force correlation. So what exactly was that, if you know the details? Because we are doing sometimes, some autocorrelation function of the motion or of dipole moment. So what exactly this force is referring to?
I was not the one who generated these data.
Okay.
What I know of them, listening to discussions with Lauren, who would really be the expert here, is I believe that they're taking the molecular dynamics simulation, they're projecting out the force onto the azide bond distance. So based on the bond distance between the nitrogen atoms in azide, they can assume what the force is onto those atoms. And so you're backing out from the distance between the atoms what the force is essentially. And then of course you're just running that force over time and then doing the correlation function of them. That's what I understand of it.
Okay, I see. Yeah, kind of makes sense. Okay. Now the one question which comes for when the motion is underdamped, so there is some oscillation. Often people try to quantify it by if you would have a look on the spectrum of that oscillation, basically the narrowness of the peak. So it's kind of quality factor, right? That's one of the basic things to characterize the. So how many cycles are there? I mean, this is roughly corresponding to the quality factor of that. Like if it's possible to.
Good question. I wouldn't have that number off the top of my head, but if I look at this right now, just looking at the time domain, I don't know, I'd say probably between 3 and let's see, so this corresponds to a 3.3 picosecond. The 908 number is a 3.3 picosecond oscillation. So I'd say maybe at best 3 to 2. Yeah, I don't know. It's a good question.
Okay. So yeah, it's very interesting. I'm also curious about these. Now when you explained that in the beginning, it was just very nice that. But maybe if you could reiterate how these oscillations actually lead to these narrower distribution of donor accepted distance. Is it still, we started the explanation with that, and then it seems you are getting to that here again, but maybe is there something missing from the MD simulations to explain that, or?
Yeah, no, that's a fair question. So the thinking is that these, you have so much compression going on in the active site that the donor acceptor distance is so narrow. But also at the same time, there's a good, we're thinking that there's an evolutionary pressure for good reason on that. We were thinking that one idea is that they're pressed up against each other so tight, but there's also at the same time, that's about an average distance. And so it's that the average distance at the center of the oscillation that we're really observing there but that there's still a lot of compression that's going on. They're just rubbing up against each other, kind of promoting the reaction to happen. So, you know, a lot of, so I have to admit, a lot of the kinetic isotope effect things and the donor acceptor distance was really, you know, preliminary to what led us to measure the center line slope in the first place. And then we found, of course, the oscillations, and then so that kind of opened up a whole new box. So it's just, you know, from a timeline of how we're thinking about things is really kind of how I presented.
Okay, I see. Well, getting back to maybe the bigger picture of this, I just actually yesterday night I finished reading one nice book about quantum biology. It's quite a serious one though. It's no esoterics, and they are speaking about these kinetic isotope effects. Basically, just saying that, you know, it's maybe straightforward for physical chemists, but basically the tunneling per se, it's, you know, a quantum effect, right?
Yeah.
So it was like demonstrating that in the core of many enzymes is the tunneling. Well, because that's temperature independent in principle.
Yeah.
And so it's just very cool on its own. So I mean, this kind of translates to the quantum biology, and I have kind of feeling that this bit beating of or oscillations which you see in enzyme side might be kind of facilitating. I mean, this is a different perspective of that somehow from the quantum perspective, facilitating this tunneling, but I'm not sure. This is how did that fit to the picture to which you presented, but kind of I feel there is a connection.
Mm-hmm. Yeah, it's you know, the thought that crosses my mind the most often is the evolutionary pressure for this to happen. Why is it that nature is so interested in having this occur? You know, these underdamped oscillations are so, in some ways, kind of unnatural to think about, but apparently not. That's not the case. And yeah, and to think that, you know, there's tunneling going on in the middle of an enzyme, it's just very fascinating.
Oh yeah, it
So
is, particularly in room
Yeah.
temperatures.
Yeah.
Yeah, it's also cool. I mean, I was asking about these quality factor of oscillations, or how many cycles are there, because it seems to be that indeed for optimal performance of the enzyme, it's not even wanted to have too many oscillations. It has to be kind of a compromise between how long this thing oscillate, and then yeah. So it's actually interesting, something I don't really understand, to be honest, but it's fascinating. So
Yeah.
okay, I see. Okay, cool. Yeah, that was great. I really enjoyed that, and obviously I will keep note of your other colleagues of your team, particularly also you meant Lauren was the one who's doing the MD simulations. So
Yeah.
I'm looking forward. I will have to follow how the things and the public papers will go out from your lab to see with the interpretation of these things, because as you mentioned, it's just quite fresh stuff, right? She was sewing, so it'll be cool to see the actual data.
Yeah.
Okay, cool. So if there's any questions from we had several attendees here. I think like up to 15 people. So that was nice. So I think it's all from my side. So Kevin, I want to thank you very much for a very interesting talk, and I'll keep you updated once we have this recorded talk on YouTube online.
Okay. Sounds
So
good.
thank you very much again. Have a good
Thank
day,
you.
and we'll keep in touch.
You too.
Bye bye.
Bye.